you are relating this angular acceleration alpha to the moment, and the moment equals to f times the distance. Suppose distance L, so the moment is just equals to f times L. But what's the direction of this alpha? This is a two-dimensional problem. I'm sorry?
In the z direction?
Yes, what's the z direction?
Coming out of the board?
Yes, right-hand rule, remember? Your four fingers goes along with the orientation of the moment, and your thumb will be pointing now to the direction of this moment. So if four fingers this way, and your thumb goes this way. So the out of the plane direction is the direction of this angular acceleration, which means what is the direction of this angular acceleration? It's not on the plane. The angular component, their directions are always out of the plane. And that's why before, when we talk about this kind of problems, you wonder, Professor, how come you didn't use these two terms? Omega z and omega y, how come you didn't never use it? It's because when we constrain our discussions on only two-dimensional problems, you don't have the angular component in other direction. You only have one direction, which is out of plane. Therefore, for two-dimensional problems, you don't have to worry about this. Because for two-dimensional problems, there's only one direction for the angular component, only one. Which is why you only have to consider the first term. You don't have to deal with these two. Now, in general, three-dimensional general motion, that may not be the case. So that's why today I'm officially introducing the complete definition of moment equilibrium in dynamics. And this is the most general form for moment equilibrium regarding angular motion. Okay. Now let's see how we actually can apply that to an example. This will be example 35. Example 35. Suppose you have a bar. Now this bar is a three-dimensional bar. Looks like this. And the bar is defined by 2 points. There's point A here, point B here. And suppose point B is supported by a hinge. Support. And we can also define the coordinate system like this. Suppose there's a vertical axis, longitudinal, and another one, of course, it goes like this to make a three-dimensional problem. Now, the question is this, and you're provided with the total length of this bar, which is 1 meter. We know this to this is 1 meter. And the problem asks you to determine, what if I want to know at this point, this is my coordinate system. So I want to define this to be the x direction, this to be a y direction, and this to be a z direction at the center of gravity, which is the middle of this bar. Right? Now, so this is my direction for the x, y, z. Of course, the same direction applies to point A, same direction applies to B. That means at point A, this is your x, this is your y, this is your z. And at point B, this is your x, this is your y, this is your z. So this one, of course, is what? Is negative z. I showed this one just to show you how the three-dimensional problem looks like. So what do we need to determine? We need to determine when this bar is spinning with respect to the z-axis at point B. Suppose this whole bar is spinning with respect to this z-axis. Of course, is going up. The direction of this omega is pointing up, not this one. But I just want to show you the three-dimensional configuration. This angular velocity equals to positive 10 radius per second. So what's the question? The question is, when this bar, remember, imagine that this bar is like this, right? So I'm going to hold the end of the bar, and I'm going to let it to spin like this. You can imagine it's going to spin like this. So I'm going to let the bar to spin like this. During this angular motion, with omega being 10 radius per second, what will be the reactions at point A and point B? Reactions means what? Means forces. And the forces, of course, must be in all three different directions, just like we defined it here. So the question is, find out the reactions. You can call it RAX, RAY, RAZ, RBX, RBY, and RBZ. So what are these? We'll just take point B as an example. For point B, this is what we want to know. This is B, there's a hinge support, right? Now, during this angular motion, I want to know that what are the forces right here? Are there any forces? Like, is this RB, this will be RBZ, right? And in this direction, if you assume either way, this will be your RBY, and in this direction is your RBX. That's the problem is about. All right, and I will finish this example on Wednesday. All right, any questions? Today we talk about determination of principal axis of inertia and that eigenvalue approach. Make sure you review the notes. I know this may be the first time for some of you seeing this kind of topic. Any other questions? If not, I will see you on Wednesday.